So all these are included in the GNSS system, like GPS, GLONASS, all these. So each of these positioning systems have different constellations and different orbits are there, and they have different frequency, and their accuracy are also different. So in today the class is about what is the GPS, what is the GLONASS, and the IRNSS and Galileo, and some part of the DGPS system, that is differential GPS. So first of all, the history of the GPS is started from 1960, and it is operational in 1964. So it has previously five polar orbit satellites. Then it's continue with other satellites. The full-scale GPS also developed in 1973, and it is also renamed as Navstar. That is a navigational system with timing and ranging global positioning systems. So previously, there are four satellite vehicles are launched in 1978, and now they are increased to 31 satellites. Then, what is GPS? The GPS is a US-based navigational satellite system, which is under the Global Navigational Satellite System. It is under GNSS system, and this global system, navigational system, having the radio navigation system, which have the radio wave, which is high wavelength uh, system, where it can penetrate through the cloud, so it is reached to the earth in very short interval of time. So this is the function of this GPS, and it has the constellation of 24 satellites. Previously, there are 24 satellites in their ground stations, and GPS use these man-made stars as references point to calculate position into accurate matter of to 2 to 3 meters. Some of the handheld GPS which are present, that is mm, as high as accuracy like 3 meter accuracy, and in giving very precise accuracy, as the GPS is very widely used GPS system. And GPS receive have been minimized due to few integrated circuits. In this day, GPS finding its way to different car, boat, planes, construction equipment. A lot of things are there. So there is some functions which GPS system used. That is, it provides user with capability of determining positioning, speed, time, and motion, and he also continuous global. This is a global coverage satellite system and all-weather three-dimensional positioning systems and high degree of accuracy. Great offer potential for civilian use. The GPS is funded and controlled by U.S. Department of Defense, and it is used by civilian use also. There's the important things about the GPS is it is used for positioning, georeference, navigation, time, frequency calibration. So these are the important things which are used based on the GPS satellites. So GPS is a Earth orbiting satellite that based system fully in operation in 1993. Signals available anywhere on the Earth, day and night, and its signals are radio waves are there, and it determines different position, altitude, and ellipsoid. And its heights, the position from the Earth is 20,200 kilometer above the Earth at the speed of 14,000 kilometer per hour. Then geoid, what is the geoid? The geoid is the shape of the earth if it were considered as a sea level surface extended continuously through the continents. The geoid is a equipotential surface. Suppose in some of the hilly terrain there is a high density, and in the core area there is a low density. So there is a equipotential um, uh, demarcated lines is there, which is covered to the total earth, that is called geoid. It is totally not overall a circle, but it is nearly circle. So this can be used as a mm, virtual earth, and their center is marked as a earth center. So from this we calculate all the latitude longitude informations. So geoid based informations are calculated in the GPS system. Then segment of GPS, different segments are there, like all GNSS system, that is uh, space segment, user segment, and control segments. Same for all the satellites. Then constellations, there are six orbital planes till now in the GPS system, and instead of 24 satellites, now there are increased to 31 satellites. There are six orbital plane, so four satellites in each plane. Now it is five satellites in each plane, and one is for backup purpose. And then incline degree is 55 degree, and the orbit height referring to is uh, medium Earth orbit. So these are some basic facts about the GPS segments. Then GPS control segments. So its control segments are spreading all over the world, and some one master control center in the USA. Then other monitoring stations are there in different areas. Then user segment, the Garmin GPS, and some mobile-based information, DGPS. All these are used by the GPS system. So basically, there are two frequency which are used in the GPS system. That is LOL frequency, that is 1575.42 megahertz, which carries the navigational message and standard positioning service code signal known as the course acquisition code, and P precise code used for the precise positioning service. Then another is the L2 frequency, which is lower than the L1 frequency, that is 1227.60 megahertz, which carries P code used for the precise positioning service. And phase difference between the P code on L1 and L2 is used to measure the ionospheric delay. So the difference between this P code L1 and L2 is calculated, and that is the error which is found in the ionospheric delays. So and there is the N1 L1 frequency and L2 frequency, and that is the L5 frequency. It is included in satellite vehicle ephemeris system times and satellite vehicle clock behavior data, status message, and time information. GPS space segment modernizing includes new signals as well as improvement in the atomic clock accuracy, satellite signal strength, reliability. Control segment modernization includes improved ionospheric and tropospheric modeling, in-orbit accuracy, additional monitoring stations. Latest generation of GPS satellite has the capability to transmit new civilian signal like designated to L2C. So there is a very long application system in this GPS. So in the new GPS system, there's a L5 frequency, which is 1176.45 megahertz is slowly being added to the new satellites. These are not available in the previous satellites. The first Napster GPS satellite to transmit L5 on a demonstration in 2009. So L5 is required for the critically safety of the life applications, and GPS satellite modernization will also include new military signals and improved L1C, which will provide greater civilian interoperability with Galileo. So the signal strength and the accuracy is very high. So gradually the different frequency bands are used for the navigation and accuracy of the precise positions. So L5 is newly added in 2009. Then GLONASS. So GLONASS is a Russian satellite system which is started in 1970s when the Cold War ended. The Soviet Union recognized that the GLONASS can also be used in commercial application. Before it, it was used as the military purpose. The first satellite of its constellation was launched in 1983 and fully operational in 1995. So GLONASS went through a period of performance decline as defined in the GLONASS interface control document. The unlimited number of air, marine, and any other type of use. Some of the satellite receivers we also find GLONASS informations. There are two dominating satellite GPS navigational satellite that are GLONASS and GPS. GLONASS from Russia and GPS from USA. So these are some of the segment. It also 24 satellites in three orbital plane. Before in the GPS satellite system, there are four orbital plane, but in GLONASS there are three orbital plane. So it is less in the orbital plane in the GLONASS system. So highest number of satellites are there in each planes. The GLONASS has also some ground control segments and space segment and user segments. So these are some monitoring stations all over the Russia. Then GLONASS coordinate system. Mm, so every GPS uses some coordinate system, that is a virtual coordinate system, which is same as the geometry of the Earth, which is imaginary surface. So the accurate definition determines process system is to assure precise positioning of GNSS. So there are ellipsoidal parameters like WGS84. All geodetic systems are also used. Ellipsoid parameter of PZ19s. So different ellipsoids informations are there, which are used by the GLONASS system. Then VIDO, which is a Chinese navigation satellite system. It is also globally coverage satellite system with 14 satellites. Video is being expanded to provide global coverage in a recent time, and the space segment will consist of 5 geostationary Earth orbital satellites, 3 inclined geosynchronous orbit satellites, and 27 medium Earth orbit satellites. Geostationary means a satellite orbit along with equator that resort at a constant fixed position over a particular reference point on Earth's surface. That is called geostationary satellite. But geosynchronous is a satellite orbit with an orbital period matching with Earth's rotation period. This synchronized means that for an observer at a fixed location on Earth and satellite in a geosynchronous orbit returns to exactly the same place in the sky. So there are six orbital plane and a total 35 satellites in video, and last launch is 2018. So these are some fact, but it is also globally coverage satellite system. So these are some basic metadata information and some basic orbital informations. So in this video, there is some radio signals are there, like GPS and GLONASS. So in this, in the GPS, there is L1, L2 bands are there. So in this, there are B2, B3, and B1, which are same as the L1 band on of GNSS signals. So the naming is different, but band are same. Signal interoperability of video with Galileo and GPS. China announced the migration of its civil signal B1 signal to 1561 megahertz to frequency centered at 1575. These are the same GPS L1 and Galileo E1 civil signal. So signals bandwidth is same, but naming is different. Then the accuracy. There are two level of service. That is for civilian and for military purpose. So for free civilian service, it is accuracy is 10-meter accuracy, and restricted military service, its accuracy is 10 centimeter accuracy. So 100 times high accuracy in the military and services. And to date, the military service has been granted for People's Liberation Army, and also service to the military of Pakistan also. Then Indian Regional Navigational Satellite System, IRNSS, most of the time the full form, this full form was also asked previously in 1 or 2 marks, 1 mark short questions, and it's also called as NAVIC. So this is a regional navigational satellite system, and the regional navigation satellite system with an operational name of NAVIC. It is called as a SELOR in Sanskrit, which also stand for navigation with Indian constellation. Is autonomous regional satellite system, and it is an independent autonomous regional navigation system, and service area about 15 kilometer around India. So buffer zone from the India is 1500 kilometer. So it also can be used by Bangladesh, Sri Lanka. So it is developed by Indian Space Research Organization, that is ISRO, which is under total control of Indian government. The requirement for such a navigation system is driven by the fact that the global navigation satellite systems GPS is not guaranteed in hostile situations. So most of the time for military operations and other emergency operations, the accuracy uh, of the signals of the GPS satellites or the GLONASS are not provided to the Indian government. So they decided to launch their own, our own navigational satellite system. So it to control all these situations. Why this is needed in indigenous positioning system? So during the Kargil war in 1999, when Pakistan troops took the position in high mountains areas, one of the first things Indian military was trying to get their hands on GPS data on the region. So they rely on the GPS information, which has a high accuracy, but GPS could not provide vital information which are used for this this work, but the United States denied and to access the military accesses, which is a high accuracy. Then the experience of Kargil made the nation realize importance of the indigenous navigational satellite system. So after that, the idea of the creation of IRNSS will begin. With the help of IRNSS, India will become the self-reliance. So after that, it is created. So in the INSS constellation consists of seven satellites. Very few satellites are there as it is a regional satellite system, and three satellites are in the geostationary orbit, and four satellites are in geosynchronous orbit. So look up in the figure, that is the uh, green circle. It is a geosynchronous, and red circle, that is geostationaries. So that means that it is likely to be stationary with respect to the earth, and it is not inclined. Geostationary orbits are not inclined, but geosynchronous orbits are inclined with the earth's uh, axis. So that is the difference. So all the satellites like IRNS-1A of the constellation are configured identically. So it has geosynchronous orbital period equal to Earth's rotation period, that is 24 hour. However, the orbit can be inclined. So geosynchronous is inclined, but geostationary is not inclined. It is a fixed over a single point of the equator, because it is a zero incline directly over the equator. So most of the things, uh, some questions are asked, what is the geostationary and what is geosynchronous. So some little bit difference is there. So this is the architecture of the IRNSS satellites. There are only seven satellites, and these are receiving in different stations. So this is the overall different satellite system, that is GPS and GLONASS, Galileo, video, RNS. So each of the satellites have different lifetime. So for GPS it is 10 years. For GLONASS it is also 10 years. For RNSS it is 12 years. So basically these are maximum 10 to 12 years lifetime. So this is the map which shows the coverage area of the IRNSS system. So from India there is 1500 kilometer, and all over the surrounding areas. So this Navig will provide accurate real-time positioning and timing services. It will cover India region extending 1500 kilometer around it, with plans for further extensions and adding some other maximum satellites to coverage more areas. In the RNSS frequency band, there is a L5 and S bands are there. So like L1, L2 bands. So different bands which are given. So some of the application of the RNSS satellite system is terrestrial, aerial, and marine navigations, disaster management, like some earthquake and other flood information, uh, flood events, and other disaster related issues are there. Then vehicle tracking and fleet management, integration with mobile phones nowadays, which is very large scale. Then precise timing, mapping and geodetic data capture, mapping purpose is also used. Terrestrial navigation aid for hikers and travelers. Uh, so all these satellites, which are navigational purpose, they have all this same application system. So according to the ISRO statement, GPS is using only L-band signals, while our IRNSS, which is also called as Navik, is using the L-band and S-band both. So since our signals are coming vertically from stationary references, our Navik is going to work better than GPS in crowded places. If we use both L and S bands, our accuracy is more than 5 meter and is very much good accuracy as compared to other satellite system. And this is better of potential for 20-meter accuracy GPS, which is actually supplemented by GPS information. When we speak about the accuracy, then Gogon, which is uses GPS signals and with additional information provided about the position of the satellite, it tells you that GPS satellite are giving you a more accurate positions in all over the world. But sometimes IRNSS system is giving more accuracy for particular crowded areas. Then Galileo is a European's own global navigational satellite system providing highly accurate positioning service under civilian control. It is interoperable with GPS and GLONASS. It is also operable along with GPS and GLONASS system. The Galileo system is uh, found later, that is in 2016. Galileo receives compute their position in Galileo reference system, which is using satellite technology based on triangulation principle. All these Galileo system are based on the triangulation principles. So Galileo satellites are terrestrial reference frame, that is GTRF, is used for Galileo navigation system. What is in a ITRF? This is International Terrestrial Reference Frame. So suppose red boundary is the real Earth coordinate, then GPS system created by the virtual Earth, that is green circles. So we created a virtual Earth. For this, there is a center. From this center, we create different latitude, longitude informations. So if the reference system is very high accuracy, then the difference between the distance between the two center point of the real Earth center point and the virtual Earth center point is very much less. So in this international frame of reference 97, there is a 2.24 meter difference between the real and the reference Earth. So it is very much accurate to get the information from ITRF, and the ITRF, that is International Terrestrial Reference Frame, is a realization of the International Terrestrial Reference and describes the procedure for creating reference frame suitable for all measurements. So we generally use the virtual Earth center points. Then from this center point, we create X and Y coordinates and Z coordinates. Another navigational satellite system is there is quasi-zenith satellite system, that is nicknamed as Michibiki, which is the regional navigational satellite system commissioned by the Japanese rocket in 2002, and it is a regional based satellite system. And the beginning of the system was developed by the Advanced Space Business Corporation team. The work was taken over by the JAXA together, that is Japan Aerospace Exploration Agency, like our ISRO. So these are the some space segment, and these are the some maximum three satellites are there, highly elliptical orbits are there. So QZSS frequency contributes various frequencies are there. That is L1 CA code, L1C, L2C, L5, L1S, and LEX. A lot of frequency informations are there. So basically, the QZSS benefits are there. There are uses in the disaster preventions, smart driving support systems, efficiency in the infrastructure maintenance, then area surveillance, landslide, railway management, city information. All these high-level accuracy systems are there. So it is used for all of different applications for regional purpose. So this is the overall glimpse of the all the satellite system, that is video, Galileo, GLONASS, GPS, Navi, QZSS. How many satellites are there? What is the frequency level which are used in the satellites? Status, precision, period, time period, the revolution time period, and then the coverage areas are there. Then the differential GNSS system, that is also one of the DGPS system, that is called differential GNSS. The commonly used technique for improved GNSS perform is differential GNSS. So general GNSS system is not much more accuracy. So that's why the introduction of the differential GNSS was used, and which is very much useful for high accuracy data information, land surveying, forest area surveying, and different plot based surveying. So in the difference between the GNSS and differential GNSS is the uh, one stationary base station is there, and one rovering rover station is there. So different satellites first receive all this data from base stations, and these are also received by the rover station, which is uh, movable. Then that transmit the range, different location range data from base station to rover stations. So after taking all these data by the triangulation method, the error of the accuracy, error of the locations are found. Then it is corrected using different softwares. And the base station the GNSS receive, which is acting as the stationary reference, which is known position and transmit message for the rover receiver to use calculate its position. So base station is very much important. It's should be in a very uh, safe position to receive all this data. So the in the base station the survey position calculated from the satellite ranges. Difference within the position can be attributed satellite ephemeris and clock errors, but mostly to error associated with atmospheric delay. So in the GPS system, we cannot avoid the atmospheric delay. So during the atmospheric delay, in the DGPS system, it is also calculated after getting all these informations with the help of rover and base stations. So there should be the needed of four common GNSS satellites which can be received by the base stations and rover system. So the absolute accuracy of the rover, which is movable, computed position will be depend on absolute accuracy of the base station. So most of the time, the base station data will be uh, reading for 2 to 3 days to get the accuracy data. So GNSS positioning absolute accuracy is the degree to which the positional object of the map confirm its correct locations. And it also advises in all the survey that the base station should not be very long with the rover locations. So the different data will be some mismatch. Then this is the function of these four satellites which are given all this data to the base station, then remote corrected position area, then there the range corrections are there. This is also one of the GPS system. Then another thing is that is real time kinematics RTK. It is also like the DGPS. The positioning technique discussed earlier as a DGNS, that is differential GNSS, is referred to as code-based positioning system because the receiver correlate with the pseudo-random codes. So earlier in the differential GNSS, there is a code-based positioning system systems are there, uh, and there are 4 to 5 satellites are there to get the information. For the RTK, there is a carrier-based phase measurement is there. So this is the difference between RTK and other GPS systems. This is the signal which is sent to the rover station and base station. The same techniques used for the RTK system, but in this there is no code system is there. There is a carrier wave for L1, that is frequency between 175, and carrier measurement is there. So base thing is basic is same, but the carrier wave and the code is different. So there are some how to calculate this clock, ephemeris, ionospheric, tropospheric delays, and advantages of the precise carriers. So what is the difference between the DGNS, that is a differential GNSS, and RTK? The configuration of differential GNSS and RTK system are similar in both the method, require base station receivers and rover. But the difference is that RTK is a carrier phase method, which is significantly more accurate than DGNSS, which is code-based method. The advantages of DGNS is that it is useful over a longer baseline distance between base station and rover receiver. But along with this, this system is less expensive. However, these conditions are changing very rapidly. The technology required to achieve the higher accuracy of RTK performance make the cost of RTK capable receiver higher than on other DNS capable only. Then another technology is satellite-based augmentation systems, that SBAS, where the application where the cost of the differential GNSS system is not justified, or if the robot systems are spread over too large area, SBAS may be more appropriate for enhancing position accuracy. So earlier in the RTA system and GNSS system, the distance between the base station and rover is maximum 10 to 20 kilometers. But in the S-base system, if the distance between the two base station and rover is more than 50 kilometers, then it is not useful. So in this case, we use the S-base system. So in the S-base system, the space segments are there, and there is a support segments are there. So in S-base support, wide area regional augmentation, even continental scale through the use of geostationary satellite, which is broadcast the augmentation information. The S-base augments primarily GNSS constellations by providing geo ranging, integrity, and correction information. These are some GPS satellites. Then this is a space segment which is constant. So this difference is calculated, then the accuracy is given in the higher accuracy. In the S-based geo satellites rely on the signal in the space because the space segment is there, but in case of other GPS there is no space segment. Their measurement and satellite position both from primary and S-based systems are applied in the S-based correction data and its integrity. So one of the S-based system is the WAS concept. There is a wide area augmentation system. The US Federal Aviation Administration has developed the WAS to provide GPS correction and certified level of integrity to the aviation industry to enable aircraft to conduct precise approach to airport. So basically, this application is useful for different uh, aviation sector. So various reference stations are there. Then these are some GPS satellites. Then there is a geostationary satellites, then the uplink station, then was message, then master stations. This is the circle of uh, measurement of all these things. So likewise, this SOS system, there is a European geostationary navigational overlay service, IGNOS. So this is a cooperation with European Commissions, and it is also augmented system that improves the accuracy of the position. The same things are there. There's a stationary satellite, then the GPS satellite, then the base station, then the user segment. So instead of baseline in the DGPS system, we mm, use baseline as a space segment of GPS satellite. So for India, that is GPS aided geo augmented navigation system. So that is called Gogon. So we have some GPS um, linked other satellite systems. So in India, we use Gogon with the help of GPS based information system. Gogon is a S-based system that supports flight navigation over Indian airspace, and the system is based on three geostationary satellites, 15 reference stations installed throughout the India, and three uplink stations and two control systems. So it is different from IRNSS. It is generally used for govern. And similarly, the same SDCM, that is called System for Differential Corrections and Monitoring, which is provided in the Russia with accuracy improvement and integrity in monitoring for both the GLONASS and GPS navigation system. Though it is collaborated with GLONASS and GPS navigation system. Then some of the ground-based automation, G-based also there. Uh, the same technology is used, that is a radio transmitter. So these are some S-based systems of different countries. For USA, that is called WAS. For a European country, that is IGNOS. For Russia, it is HDCM. For China, sorry, for Japan, it is MSSC, MSSS, and for India, it is called Govan. So in the S-based system, there is suitable application for the cost of installing a base station is not justified. If some of the area that is not justified for base station, if the robot station are spread over too wide area, so in that case we can use S-based system. But S-based system has less accuracy as compared to other base station based in differential GPS. So this is a summary of S-base, that is it is geosynchronous satellite system that provides service to improve the overall GNSS accuracy, improve accuracy through wide area correction of range errors, enhance integrity through integrity monitoring data. So frequently the data is updated for geostationary satellites. Then they improve signal available for S-base transmit the ranging. SBS has two level of service, that is pre-government to provide SBS service in GPS frequency and commercial SBS service in different frequencies. So different free SBS service are available around the world. Wide area augmentation, that is useful for North America, then European, that is IGNOS, then Canada and continental United States. MTSAT, GPS aided augmented navigation system, that is governed for India. So these are some example of the S-based system. Then GPS error sources. So how many errors are there? That is called satellite clock error, orbital error, ionospheric error, delays, tropospheric delays, receiver noise, multipath. So these are calculated in meters. So in the satellite clock, if the clock error is arises, then it has shifted to 2 plus minus 2 meter accuracy. Then for orbital errors, it is plus minus 2.5 meter error range. Then ionospheric delay, it is most of the highest error range, that is plus minus 5 meter. Tropospheric delays, it is very less error range, that is plus minus zero point 0.5 meter, which is 50 centimeter. Then receiver noise is plus minus zero point 0.3 meter, and multipath, that is plus minus 1 meter. So these are the errors which are generally found in the navigation satellite systems. But all these errors are not found at a time. So sometimes the ionospheric delays have some issue. In some cases, the orbital error is some issue. Then multipath error is also there. So some cases there are two, three errors are found, but in some cases there is one or two cases are found. So in the satellite clock, the DNSS satellite are very accurate, but they do drift some amount, very less amount drifted. In some in small inaccuracy in the satellite clock result into significantly error in the position calculated by the receivers. So, for example, 10 nanosecond of clock error result in 3 meter of position error. So, if the 1 second of the error is found in the satellite clock, then it is thousands meters of error. So, orbital errors, GNSS satellites travel in very precise, well-known orbits. It is however, some of the time the orbit also drifted due to some factors. So, like the satellite's clocks, a small variation in the orbit result in a significant error in the positioning calculation. So, global navigational satellite system, ground control system, continually monitoring the satellite orbits for their error, and when the satellite orbit changes, the ground control system send a correction to the satellites, and the satellite ephemeris is updated. So if there is any orbital changes are there, then it is corrected immediately. Then the ephemeris data also, which are um, including the all the orbital information, that is updated. Then it is corrected as much as possible. Even with the correction from the GNSS ground control system, there are also still some error in the orbit that can result up to plus minus 2.5 meter of original error. Then ionospheric delays. So when the signal is passes through the ionosphere, a lot of metal particles are there. So there is a chances of deflection of the signals, and the time interval also increases. So it is found in that 80 to 600 kilometer above the Earth's surface, which is the electrical charge particles, that is ions. So it's get the error of plus minus 5 meter. When it is high ionospheric activity, then the error is very high. So generally the ionospheric delays varies with the solar activities, time of years, season, time of day, and location. This makes it very difficult for predict how much ionospheric delay is impacting the calculated positions. So ionospheric delay also varies based on the radio frequency of the signal passing through ionospheres. So basically, as the electrically charged particles are there in the ionospheres, the signals passes through this layer. The penetration of this signal is very high, so there is some time delay, and due to this, there is a error found. Then tropospheric delays, like the ionospheric delays, there is also a delay in the tropospheres. This allow differential GNSS RTA system to compensate for tropospheric delays, and the GNSS receiver can also use tropospheric model to estimate the amount of error caused by the tropospheric delays. So some of the errors are calculated using different models. Then it is commonly found in the survey systems in the urban areas basically, and the hilly areas also, the multipath. So if the signal received in the receiver is not directly from the satellite system, and it is diverted from a different structure, then the delay in the time, and this due to this delay, the accuracy of the position is also affected. So simplest way to reduce the multipath error, it is place a GNSS antenna in a location that is always away from the reflective surfaces. When this is not possible, the GNSS receiver and the antenna must deal with the multipath signal. Multipath occurs when the GNSS signal is reflected off in objects such as wall of the buildings and GNSS antennas. This is also one of the example of multipath error. So instead of direct receiving from GNSS satellite, of receiver, it is reflected back from these buildings and received. So this is some error found. Then how to correct all these errors? So precise point positioning system is there. There is techniques that is remove or model the GNSS system error to provide high level of position accuracy from single receiver. Then the precise point position solution depends on GNSS satellite clock and orbit corrections, which are generated from network of global reference system. Once the corrections are calculated, they are delivered to the end users via satellite and over internet. So this is the precise point positioning systems. In this, the geostationary satellites give the information to the reference stations, and all GLONASS or GPS satellites give the information to the reference system. Then it is also give the link to the all information to the ground uplink substation. Then it is transmit to the geostationary satellite. So in this method, we calculate the error, then it is corrected. And dual frequency operation is one of the criteria to correct the operation. Suppose in the tropospheric or ionospheric layer, L1 frequency passes through this layer, then L2 frequency. So they have the different wavelength. So for smaller wavelength, it passes in the uh, later way. So the time difference is calculated for different frequencies. Then the error are calculated. Then it is corrected. And some of the corrections using terastar. So there are some satellites are there in the equator. Terrestrial coverage maps are there. So using this reference system, the correction are made. Then PPP filter algorithms are there. Then Genesis data post processing also there in the post processing system, and with the triangulations methods, uh, the accuracy is calculated. This is the post processing system software, which is measured in according to the mission. So using this technology, the accuracy and the precision is calculated. So this is the comparison accuracy of practical range of use of different methods. So after correction of all these satellite information data with the different technology and methodology, so we found that these are the some frequently and the average accuracy of the all the system, that is RTK is a high accuracy system from 1 centimeter to 8 centimeter. Then PPP system is 10 centimeter. Then DGNSS, there's a differential GNSS is 1 meter to 5 meter accuracy. Then SBAS is a fixed accuracy system, that is 1 to 2 meter. Then GNSS of all other satellites, which has 10 meter accuracy. With some of the DGNSS and RTK system, the difference between the SBAS and PPP. Then DGNSS is a system required for station receiver and antenna, but SBAS has no require of station-based antenna. Then RTK system offer higher accuracy and quick initiations for more complex, but is PPP has a simplified configuration system. So in general, GNSS receiver are used to collect position, velocity, time information for various applications. In some specific cases, the other measurements output by the receivers are also used. The receivers might be generic all-purpose receivers and can be built specifically having the application in mind. The initial objective of the first few GNSS systems are for use in the military purpose, or after the free available of GPS and GNSS signals, then it is also used in the civilian purpose and industrial and scientific purpose. So location-based services includes application that depends on the user location to provide the information that is relevant to the user at that time. Then LBS is normally used mobile devices. Different type of LBS are location-based information, then tourist information, transport and demand. These are some of the applications. Then civil applications like personal application, road application, aviation application, rail application, maritime applications. So movement of the sea and industry-based applications are there for the GNSS system. So nowadays there is a large of applications are there using this GNSS system, and for getting the high accuracy survey, so we use the global mm, positioning system with a differential positioning system, that is line surveying and aerial surveying. In the some cases, the earth sciences also uses the GNSS system, that is studies for groundwater deformations, millimeter accuracy position required, support for global earth science application like global distribution tracking network needed, then atmospheric effect analysis of propagation of delay of signals. So, with the help of the GNSS, the movement of the India's plate also measured for each year. So, according to this, there is a shift of the Indian plate every year, very slightly. Some of the stations are there which are located in the Indian map, and this is the movement of the Indian plates in the northeast direction. So, this is found that the movement of the Indian plate is 5 centimeter per year. So it is a very fast moving according to the geological studies. So it is also calculated by using the different differential navigation system. So apart from this, there is also meteorological application system. Uh, so neutral atmosphere, water vapor, delay, charge particle layer, ionosphere, variation effect of radio communications, power grid. So a lot of applications are also there in the meteorological applications. So nowadays, a lot of applications are there in the present scenario, like ground waters prospect, recharge zone mapping, national WhatsApp, wetland map monitoring, national wetland inventory assessment, coastal zone studies, uh, then biodiversity, urban information system, water resources, SHDP, natural resource sensors, flood mapping, watershed mapping, and potential fishery. Primary applications in the GNSS is Earth system deformation measurement, continuously operating network supply direct measurement of deformation, but also support densification of networks using occasional observations. Contribution which improve accuracy in region. So earthquake, volcano, weather system, all these are monitoring with the help of GNSS system. So after all are applications used for GPS navigation system. So the GPS part is completed. So basically, from this part, the questions are arises like how much, what is the different segments of GPS, how many GPS system are there, and GNSS system are there. So they are asking the questions about the GNSS system. So in the GNSS system, we have to write different GPS satellite, GLONASS satellite, then different regional satellites, naming functions, along with the uh, technology provided mm, with these systems and different applications with the help of these GPS systems. So sometimes these long questions are asked, and some soft questions like how many satellites are there, then what is the height of the GPS satellite, what is geosynchronous and uh, geostationary satellites, then the navigational satellite system has the different L1 and L2 bands. So these type of questions are arises in this part. So be prepared and just read all these IGNU books, and I will provide all these presentations after completing all these uh, classes. So next class will be the GIS, basics of GIS. So today's class is completed. So if there is any queries or any question asked, then you can ask. Okay, then we will conclude all these classes today. Amit
हेलो।
Kumar.
हाँ सर,
Okay, then
प्लीज शेयर दिस पीपीटी सर।
okay, I will provide you all this PPT uh, tomorrow. Okay,
बट बट सर, ये पीपीटी मतलब आप शेयर करते हो, पिछली वो जो लास्ट क्लास में भी वो मिली नहीं सर।
last class.
हाँ, कल की जो क्लास हुई थी
हाँ, मैं एक
उसकी
साथ
पीपीटी।
दोनों का सेंड कर दूंगा। ओके।
ओके।
हम्म।
ओके सर, थैंक यू सर।
और बाकी सब पीपीटी मिल गए।
बाकी अभी
राकेश सर का।
राकेश सर की भी नहीं मिली पीपीटी।
और उन्होंने नहीं दिया। उन्होंने दिया था शायद।
अब
दो
वही तो मैं
पीपीटी
पूछता हूँ
शायद
कि ये
दिए
पी,
थे।
हाँ पीपीटी वो मतलब सेंड हमें मिलती नहीं है कि कहाँ कहाँ जाती है, यही पूछ रहा था मैं सर।
नहीं नहीं,
पीपीटी अगर शेयर करते हैं तो
अभी जो वो है ना पीजी डीसीए 2024 जो व्हाट्सएप ग्रुप।
उस ग्रुप में या तो फिर मैं ऐड नहीं होऊंगा।
अच्छा, आप में ऐड नहीं है तो अभी पूछ लीजिए आपसे, जो कॉलीग है। प्रीवियसली मैंने तो नहीं दिया था। मैं कल भेज दूंगा। अगर कल नहीं मिला होगा तो देखेंगे। ओके।
सर वो ग्रुप किसने बनाया ये भी नहीं पता।
नहीं, मुझे भी नहीं पता। मैं भी ऐड किया हूँ लास्ट में। मैं तो प्रीवियसली क्लास नहीं करता था। तो पूछ लेना अभी। फिर आपका नंबर क्या है, नहीं तो मैं ऐड कर दूंगा।
जी जी, मैं नंबर बताता हूँ सर अपना।
हाँ।
9873
हम्म।
9989
हम्म।
77।
हम्म।
9873 9989 77।
नाम क्या है? अमित कुमार।
जी।
ठीक है, मैं ऐड कर दूंगा। ओके।
ओके, थैंक यू सर।
थैंक यू। थैंक यू। गुड नाइट।
गुड नाइट।